In this class, we will discuss common approaches that are used to follow up a significant finding in ANOVA models. One of the advantages of the ANOVA models over the t-test is that we can evaluate more complicated experiments. In a t-test, we can only test null hypotheses concerning one or two means. But in ANOVA, we can test hypotheses from experiments involving two or more means. For example, in the class on the one-way ANOVA, we tested a null hypothesis concerning an experiment using a single independent variable with three levels: experimental group, standard treatment group, and a no treatment group. If you recall, the null hypothesis was that the mean BDI scores were equal across all levels of the independent variable in the population. Although the analysis of variance can tell us whether a complex hypothesis like this one can be rejected, when there are more than two levels to the independent variable, it cannot tell us exactly where differences lie. In this example, used in class, the ANOVA was able to tell us that the three means did not equal each other, but it could not tell us where they did not equal each other. It is possible that the null was untrue because the mean of group 1 was lower than the mean of group 2 or 3, or it's possible that the mean of group 1 is lower than the mean of group 2, but did not differ from group 2. And finally, it's possible that the mean of group 2 is lower than the mean of group 3. Thus, the rejection of the overall null hypothesis for the ANOVA left us with three smaller pairwise null hypotheses. The first null hypothesis is that mean 1 equals mean 2 in the population, mean 1 equals mean 3 in the population, and mean 2 equals mean 3. While it is possible to do a series of t-tests to compare the pairs of means, this approach actually increases the risk of making a type 1 error. For example, if we used a t-test to test the three possible comparisons in our example with alpha set at 0.05, our risk of making a type 1 error somewhere in the set of comparisons actually increases from 0.05 to 0.15. In fact, our risk of making a type 1 error across the set of or family of comparisons, and that's the alpha with the subscript FW family-wise, can be computed by multiplying the alpha rate per comparison by the number of comparisons. So if we added another group to our experiment, the number of possible comparisons increases to 6, and the alpha rate family-wise increases to 0.30. In this class, I will discuss two types of solutions to the problem we face when following up a significant analysis of variance finding when we have three or more means. The first solution is often referred to as simply a Bonferroni approach, named after the famous mathematician. In this very popular follow-up technique, we avoid the increase in family-wise type 1 error by forcing the family-wise alpha to remain at 0.05 and simply reducing the alpha rate per comparison so that the family-wise error will not exceed 0.05 when we evaluate all hypotheses. So if we have three means, we would divide 0.05 by 3 and come up with 0.017. This would be the alpha rate per comparison for tests of three different sets of pairwise means. Before going to the next slide, see if you can answer the following question. If we were following up a significant overall ANOVA with 4 means and thus 6 possible comparisons, what would our alpha rate per comparison be? The answer is 0.008. Thus, if we perform 6 comparisons, each with alpha set at 0.008, our overall risk of making a type 1 error across the entire set or family of comparisons would be retained at 0.05. You will see the Bonferroni used very frequently as a follow-up test, as it ensures that our risk of making a type 1 error remains at the desired level of 0.05. However, you may remember that when alpha is lowered, as alpha per comparison is lowered in the Bonferroni, we pay for the added protection against a type 1 error with a concomitant increase in type 2 error. To see why that is, consult a t-table and compare the critical value for a two-tailed test when degrees of freedom equal 10 and when alpha is 0.05, and when alpha is set at 0.001 for the same degrees of freedom. See if you can locate the two critical values before going to the next slide. Consulting the t-tables, the critical values when degrees of freedom equal 10 and alpha is equal 0.05 is a plus or minus 2.228. And when alpha is increased to 0.001, the critical value is plus or minus 4.587. Thus, when alpha is increased, the critical value increases, making it harder to reject the null hypothesis. For this reason, our risk of making a type 2 error increases. To use an analogy, if the critical value is a hurdle that has to be overcome to reject the null hypothesis, the hurdle has been set higher and is more difficult to overcome when alpha per comparison is decreased. Because follow-up tests protect against the increase in type 1 error family-wise in a number of different ways, we will speak of follow-up tests as existing on a continuum from conservative to liberal. A conservative test emphasizes protections against type 1 error at the expense of increasing the risk of type 2 error. In contrast, a liberal test emphasizes protection against a type 2 error while setting less rigorous standards for avoiding a type 1 error family-wise. The Bonferroni is generally considered a conservative follow-up procedure. Another approach to the follow-up of a significant overall ANOVA is a family of procedures called multiple comparisons. These procedures test all possible pairs of means or all possible pairwise comparisons. In general, they work by establishing a critical distance between means when they are arranged from lowest to highest. A comparison of two means, or a pairwise comparison, is said to be significant if the difference between the two sample means exceeds the critical distance. There are many multiple comparison procedures, and they are generally referred to by the statistician who developed them. Examples include Tukey's test, Dunn's test, the Newman-Kuhl's, and Chaffee's test. Like Bonferroni, they vary in terms of how liberal versus conservative they are. The Chaffee's test is regarded as a very conservative test, while the Newman-Kuhl's and the Dunn's tests are quite liberal. Tukey's falls somewhere between these two extremes. The results of a Bonferroni or multiple comparison follow-up to a significant overall ANOVA can be presented in many ways in the research literature. At this time, the most common method of presenting findings is the subscript method. In this method, researchers present the group means, then put a small letter subscript on means that were not found to be significantly different or that we failed to reject the null hypothesis for. For example, let's take our original experiment with 3 means. Remember that in the follow-up test we explore all pairwise comparisons. Here our first null would be that the mean of group 1 equals the mean of group 2 in the population. The second null would be that the mean of group 1 equals the mean of group 3 in the population. And finally, that the mean of group 2 equals the mean of group 3 in the population. Let's say we performed a Bonferroni follow-up to the significant overall ANOVA, and that we found that mean 1 was less than mean 2 and mean 3. Let's also say we found that mean 2 did not differ from mean 3, or that we failed to reject the null hypothesis for this pairwise comparison. In this case, we would place a subscript A next to the means 2 and 3 to indicate the null was not rejected, or we might say that we were not able to confirm a statistically significant difference between the two means. No other subscript would be used because mean 1 was significantly lower than means 2 and 3. Let's try another example. Imagine we have an independent variable with 4 levels or 4 means as shown in this slide. There are 6 possible pairwise comparisons in this set of means, each with its own null hypothesis. Our null hypotheses would be as follows: mean 1 equal to mean 2 in the population, mean 1 equal to mean 3 in the population, mean 1 equal to mean 4 in the population, mean 2 equal to mean 3 in the population, mean 2 equal to mean 4 in the population, and mean 3 equal to mean 4 in the population. Now imagine that we found that mean 1 was higher than 3 and 4, but did not differ from mean 2. Also, we found that mean 2 was higher than 4, but did not differ from 3. And finally, that mean 3 was higher than mean 4. Before going to the next slide, see if you can supply the subscripts for this problem. The answer is that means 1 and 2 would share a subscript A because the test of that pair of means did not reject the null. In addition, means 2 and 3 would share a subscript B because the test of that pair of means did not reject the null. Mean 3 would not share a subscript A with group 1 because they were significantly different, or the null hypothesis for that pair of means was rejected. There is no subscript associated with the mean for group 4 because it was significantly lower than all other means.